to record today's class because the class earlier got interrupted by the fire drill, and we had some important stuff to do. So, we can hit the door, and I'm going to get started with our plan. So, we have 3 weeks until your exam. Yes! Now, there's a real reason that I do exams before Christmas. The reason is that you get to take the exam while everything's fresh in your mind. Thing number one. Then you get to work hard, you get to do it, complete it, go across the finish line, and then relax over Christmas break instead of having this exam to look forward to after Christmas and all that stuff. Trust me, in January you're going to be really happy that you took your exam at Christmas time. Our plan for the next week is to finish derivative rules. And we're going to be doing that for 5 days. We need to talk about exponentials and logs. That's the only thing left. And then after that, we're going to use derivatives to sketch graphs of functions. Right now, if I ask you to graph y equals f of x, you basically have to look it up in your mind and say, is this a linear function? Is it a quadratic function? Is it a trigonometric function? Something like that. What we're going to do is to get general calculus tools that will let you sketch the graphs of all manner of functions, even if you've never seen that particular type of function before. Well, as long as you know derivative rules. So, we're going to work on that for probably a week and a half. And then at the end of that time, we'll do a couple of days of review, and then your exam is going to be either on the 19th or 20th. I need to negotiate with the other AP teachers to find out exactly when. So that's our plan. That's our big picture plan for the next 3 weeks. For today, we're going to do a little bit of review of inverse trig functions. Then I'm going to talk a little bit about exponentials and their graphs. And their algebra. And if we have time, I will talk about the special base E, which has a really interesting history related, of all things, to banking and finance. So we may get a chance to do a history lesson on E here, but whether we do or not, we are going to then focus on e to the x, and in particular, we're going to try to end the day with a derivative rule for the exponential e to the x. Okay? That's our plan. Question? Okay. Good. All right, well, let's do a review of the inverse trig functions. We learned a lot of material last week about the inverse trig functions, but it can all be boiled down to our derivative rules. The bottom line is that you need to know the derivatives of what I call the big three: inverse sine, inverse tangent, and inverse secant. And these are as follows. And last week we developed each one of these formulas through a process. And I'm actually going to walk through that process in just a minute for inverse secant so that you can know how to derive them. Students often see these complicated inverse trig function derivatives and ask, exactly how should I learn them? And I recommend kind of a hybrid approach. On the one hand, you definitely want to have those memorized. On the other hand, memorizing them just by trying to memorize the forms is probably not going to be very successful. So I would recommend quizzing yourself on them, but if you do not know it, then derive it with the process that we walked through. If you have these three, the derivatives of the inverse cofunctions are easy because they are all the opposites. The derivative of inverse cosine is negative 1 over root 1 minus x derivative of inverse cotangent, negative 1 over 1 plus x squared. And the derivative of inverse cosecant, negative 1 over absolute value of x, root x squared minus 1. So really, you just have to know 3 of these and a simple fact, and you're good for all 6. So let's say hypothetically that you forget one. Let's say that you forget the derivative of inverse secant. And so you have to prove it to yourself again. Remember that we had a process for generating things, and we started by undoing the inverse trig function by taking the secant of both sides, like so. Remember this?
Yeah.
Then we differentiate. In this particular case, we take the derivative with respect to x of secant y. On the right side, we get 1. On the left side, we get secant y, tangent y, that's the derivative with respect to y, but now, how do I make it? Times dy dx. And then there's our chain rule happening. Because I'm taking a derivative with respect to x as a function of y. So that dy dx is 1 over secant y times tangent y. This is a perfectly good answer, but it is in terms of y. So we are going to take that answer in terms of y and express in terms of x. And we're going to do that using trigonometric identities. Observe, first of all, that secant y is x. So I can replace the secant y here with x. What about the tan y? So the tan y I'm going to remember the Pythagorean identity, tan squared plus 1 is equal to secant squared. And I'm going to solve for the tangent right. So that tan y is equal to either plus or minus the square root of secant squared y minus 1. Now, a few things have to happen. First of all, I need to again observe that secant y is x. So this is the same as plus or minus the square root of x squared minus 1. That's the first thing. And then the second thing that I need to do is I need to decide plus or minus. And the answer, strangely, is that it depends on what x is. If you take a look at the graph of y equals inverse secant, which we graphed last week, it has the special point 1 comma 0. It has the special point negative 1 comma pi, and it has the horizontal asymptote y equals pi over 2. So the graph goes like so. You can see that this graph has positively sloped tangent lines for all values of x. Positively sloped tangent lines for all values of x. And so that means that when x is positive, I need to take the positive root. But when x is negative, I actually need to take the negative root in order to have a positive slope. Well, we have a function that is positive x when x is positive and opposite of x when x is negative. That's the absolute value. So that we will take the absolute value of x here in order to guarantee positive slopes of tangent lines for all values of x. Does that make sense? This absolute value here is a special wrinkle that occurs only with the secant and, of course, the cosecant. In the case of the cosecant, we want the slopes to always be negative. So we have the slope as -1 over absolute value of x, root x squared minus 1. That's the short of it. Are there any questions about inverse street functions? Okay. Well, let's talk exponentials. I'm going to begin with a review of stuff you did last year. An exponential function, for our purposes, is going to be a function y equals b to the x. And we're going to call b is the base of our exponential. And we're going to place a requirement on b that it be a positive number. And the reason that we place the requirement on b that it be positive is so that our domain, a set of all x's that we can legally substitute in, is going to be all real numbers. If we did not make this requirement that b be positive, for example, if we let b be negative, then certain exponents would be illegal, like 0.5. A negative number to the 0.5 power is the same as a negative number to the 1/2 power, is the same as the square root of a negative number. Not a real value. So we require that our bases be positive. Now, when we talk about b to dx, the first thing that we're interested in is the graph. What does the graph of y equals b to dx look like? You sort of have a slash, yeah, like that. Exactly. Is it always increasing? Can it be decreasing? Can be decreasing. If it's decreasing, it looks like so. What are the conditions on b that tell us whether my exponential will be increasing or decreasing? No, all b's are positive, so that takes care of that.
Is that like larger than 1?
Yes, that's exactly it. Our function b to the x is going to be increasing if b is greater than 1. Think about it like this. Take a value larger than 1, say 2, and raise it to the x power. As you increase the exponent x, you will get larger and larger values. But if b is between 0 and 1, then b is a fraction less than 1. When I raise that fraction to larger and larger powers, it's going to get smaller, and the result will be smaller and smaller, closer and closer to 0. So we have two different shapes of graph. And when we're graphing, I recommend a 3-point solution here. You can always find 3 points on this graph. First of all, every single exponential is going to go through the same point 0, 1. Because b to the 0 is equal to 1 for all positive b. Second of all, every single exponential is going to go through the point 1, b. And this is a way to check yourself on the shape of the graph, because if b is less than 1, then the point 1, b is going to be below the point 0, 1. And if b is greater than 1, the point 1, b will be above the point 0, 1. And the final point is not a point, but a horizontal asymptote. In particular, you can see that the limit as x goes to negative infinity of b to the x is equal to 0 for b greater than 1. Or, get rid of this spare line right here. Or, you can see that the limit as x goes to positive infinity of b to the x is 0 when b is between 0 and 1. So, Notice that this is the very first time that we have encountered a function in the family of functions that we're familiar with that has a horizontal asymptote on one side only, either to the right or to the left, but not both. All of our rational functions that had horizontal asymptotes had the same horizontal asymptote on both sides. And now we have a function that is a horizontal asymptote on the right side only. Yes?
So always one side.
Well, it has to be, because you can see, for example, as x goes to positive infinity for b bigger than 1, that limit will be infinite. And as x goes to negative infinity for b less than 1, that limit will be infinite as well. Look at the shape of the graph. Yeah? So one side only. So that's the graph. Questions so far? Okay. Good. Yes.
So when b is greater than 1, then x goes to negative infinity. But it never comes to x equals 0 then.
That's correct. The range of our exponentials for all values of b is 0 to infinity, not including 0. And the reason for that is very straightforward. There is no power that I can raise b to in order to get a negative number. A positive number raised to any exponent will always be positive.
It doesn't include 0.
Yes, the limit is 0. So what that means is that b of x is arbitrarily close to 0 for x's that are sufficiently negative. But it is never 0. And that's reflected in the fact that our range is the range, the open interval, 0 to infinity. Good? Okay, good question. Let's take a look now at the algebra of exponentials. These are very familiar to you guys. The product, quotient, and power rules for exponentials. What are they? B to the x times b to the y is the same as? That's right. Because I am simply counting factors of b. B to the x times b to the y, at least for integer x and y, would mean b times b times b x times b times b times b y times. And so I count them all up and I have x plus y factors of b right here. Whereas the quotient rule is canceling factors of b, so b to the x over b to the y is the same as? Now I'm counting factors of b to the x, so I get. Now here's a fancy thing. Notice that multiplication is commutative, so this is the same as b to the yx, which is going to be the same as b to the y to the x power. So notice that I can reverse my order of exponents here if I need to. So these three properties then are used for exponentials all the time. In addition to the three properties, we also have an inverse. And the inverse of the exponential is log base b of x. Now we're going to spend a lot of time on Wednesday and Thursday talking about logarithms. Today, the only thing that's interesting to us is the property of logs, the solving property, which comes straight from the fact that the log base b is the inverse of the exponential b. These two functions cancel to give you x. So we use these functions algebraically like this. Suppose we have some equation such as 3 times 2 to the x equals 4. Then I can solve this equation by first isolating the exponential, dividing both sides by 3, and then undoing the exponential with the appropriate base log. These cancel, and I get x. Correct? Now, what is the log base 2 of 4/3 as a number? That's a perfectly good number. I'm just going to leave it. If I need a decimal approximation, I can get one from my calculator, but usually I don't.
What is the base 2?
Ah, because my exponential was of base 2.
If you go like base 10, then you look at x equals to log over 3 over log.
Yes, you will, where the logs are in base 10. So what you just did was you discovered a change of base formula.
Are they the same?
They're the same value. Exactly right. Here, all I'm doing is using log base 2 as the inverse of 2 to the x. Does that make sense? And next. Yep, take purple pass. Okay. Yes, sir.
Then just take a root.
Can you take a root?
I mean,
Well, if you wanted to take a root, the root you would have to take would be the xth root. And when you did, you would not solve for x, but instead you would find 2 is equal to the xth root of 4/3, which doesn't tell you anything about x. It's a true statement, but it's not helpful. You see? So notice that a log is really different from a root. You see it?
I was confused. 2 and x.
Yes, that's right. If instead I had the equation x squared equals 4/3 with x greater than 0, then x would be the square root of 4/3. Notice the really different role played here by the exponent and base. Yeah. So this is not that. Good question. Okay, any other questions? Let's do a little bit more advanced example. Like so. Now here, I'm using the base e. E is a very special number that I'm going to talk about a little bit more later on in this lecture. E is an irrational number, meaning that its decimal approximation does not terminate and does not repeat. And for reasons that are not yet clear, but will become clear over the next week, E is actually the preferred base for our exponentials because it has a couple of special properties. And its inverse of e to the x is, of course, log base e of x, but we're going to use a special symbol for it. We're going to call it the natural log of x. And again, it's not clear yet why that's called natural, because it seems a little bit unnatural to be using such an irrational base. But when we explore the properties of natural log, you'll see why we actually prefer to use that base. So if we're solving here, then we're going to do the exact same plan that we had previously. We're going to isolate the exponential. So here's my original equation. We're going to isolate the exponential by dividing both sides by 3. And now we will take the natural log of both sides as the inverse of e to the x. These cancel, giving me the exponent, which is x minus 2. And now you can add 2 to both sides to get your solution, which again is a perfectly good number, and I don't need a decimal approximation. Yes, sir?
Because low b x is equal to inverse b.
Yes, exactly. Exactly. Good. Any other questions? Sometimes we can be fancy. I'm going to do one more algebraic example. Yes, sir.
So inverse of e to the x equal to ln
X. Exactly.
So
Which is the same as log basic.
so that means the inverse of ln x equal to e to the x.
Exactly. That's right.
Thank you.
If f is the inverse of g, then g is automatically the inverse of f. Here's one more algebraic example. This one seems wild. There is no hope of trying to solve this with a natural log because I can't isolate the exponential. But Jason has an idea. What's your idea? Ah, very good. That's exactly right. So we notice that e to the x to the 2x is the same as e to the x quantity squared. So what I have is a quadratic that can be factored. E to the x minus 2 times e to the x minus 1. That's very good. Now I can appeal to the zero product property and say that either e to the x minus 2 is equal to 0, or e to the x minus 1 is equal to 0. In the first case, that would tell us that e to the x is equal to 2, and so x is equal to the natural log of 2. Notice that again I'm using the inverse properties here. This would tell us that e to the x is equal to 1. What exponent is x if e to the x is 1? Exactly. So we can say either that x equals natural log of 1 or 0. So the key feature here was to cleverly use our exponent rules to rewrite e to the 2x as e to the x squared and to recognize the quadratic. Okay, well enough about the algebra unless you have questions. Let's talk now about the calculus. And at this point, get your calculators out. We're going to calculate a limit. Let's see here. All right. 20 minutes. Yeah, I'm going to spend our time on the special limit and derivatives, and then I'm going to save the history lesson for another time. What I'd like to do is to calculate a special limit that is going to be special limit number 3. Now we've had 2 special limits already. Special limit number 1 was the limit as x goes to 0 of sine x over x. What was that limit? 1. And the second special limit was the limit as x goes to 0 of 1 minus cosine x over x. What was that limit? 0. So this is our third limit. The limit as x goes to 0 of e to the x minus 1 all over x. What I'd like for you to do now is to use your calculators to estimate a value for this limit. Don't forget to look at both left and right hand sides. Go. Okay, yes, so by checking both sides, you can see that the limit appears to be 1. We are going to accept this as a fact without proof. Because the proof would really take us off topic here. But what we're going to do now is to leverage this special limit in order to find the derivative of e to the x. And the derivative of e to the x turns out to be delightful. So, since we don't have a derivative rule, we are going to have to use the limit definition. The limit, as h goes to 0, of e to the x plus h minus e to the x all over h. Take a minute there, check that we have our difference quotient, f of x plus h minus f of x all over h, as h goes to 0. 1.
Oh, f of x plus h.
Yes, exactly. So notice that the argument, f of x plus h, the argument x plus h is found right here. Okay? Now, we're going to use some exponent rules, because e to the x plus h is the same as, e to the x plus h is the same as what?
Times e to
Give me the whole thing?
the x times e.
Exactly so. So there is our use of the product rule for exponentials, the algebraic product rule for exponentials. And now what I observe is that these two terms here have a common factor of e to the x. And since that common factor of e to the x does not depend on h, it is a constant, and I can pull it to the outside as e to the x times the limit as h goes to 0 of what's left? First term?
1.
What's first term?
E to 0.
E to the h minus
1.
1 all over h. But hey, we know this limit. This is our special limit that we just calculated. What's its value? 1. So that this whole thing goes to 1, and look at what we're left with. The derivative of e to the x is e to the x. The derivative of e to the x is itself. What an interesting and fascinating result. Yes.
Can you throw power in this?
Yeah, sure can. That's a great thing to do. Jason wants to check this against the graph of e to the x. And here it is. First of all, is e of base bigger than 1 or less than 1?
3.
Bigger. So our graph is going to look like this. And it's going to go through the point 0, 1, and through the point 1, e. And it looks like that. And so what we're saying is that at every point on this graph, the slope is equal to the y value. So at this point 0, 1, the slope of the tangent line is 1. At this point, 1, e, the slope of the tangent line is equal to e. Just like so. Yes?
I'm going to take this out.
Ah, because e to the x does not depend upon h, it is a constant with respect to h. In other words, as h goes to 0, e to the x is going to remain e to the x. Wow, that's a really cool result. Now, immediately I have to warn you, students will not pay attention sometimes, and they will look at this and they'll say, oh, this should work just like the power rule. And every year I get at least one student that tries to tell me that the derivative of e to the x is x e to the x minus 1. It's not. And the reason that it's not is that the variable is in the exponent now. It's not in this. So the power rule cannot possibly apply to the exponential function. And that's where you have to be careful. Okay? Yes?
So variable is on that base, it doesn't matter, like we can use.
Yeah. Okay. Wow, that was global. Okay. So what happens now when I differentiate functions that are exponential, like so? When I differentiate an exponential function, the exponent is the inside function. So I'm going to think of this as a chain rule situation in which I have an outside function, exponential, times the derivative of the inside. So we're going to treat this like we would any other chain rule situation. The derivative of the outside, e to the x, is itself. In this case, e to the 2x, times the derivative of the inside. Just like so. This works for even more complicated examples. This is a famous function, e to the negative x squared. Have any of you taken statistics? The shape of the graph of e to the negative x squared is called bell curve. And we have to do a little bit of parameters on the inside with it. It's basically the normal distribution curve. Right? So if we were to take the derivative of e to the negative x squared, we would treat this again as inside, outside. The outside is e to the flat. The inside is negative x squared. So the derivative is the derivative of the outside times the derivative of the inside. Just like so. Notice that the derivative of the outside is particularly easy because it will always be exactly the same thing that you have right here, because the derivative of e to the x is itself. In what way is it the inside function? Think of it like this. Suppose I have f of x equals e to the x. Now, what is f of negative x squared? Well, that would be e to the negative x squared. So the outside function is the exponential. The inside function is the negative x squared. So d dx of f of negative x squared would be f prime of negative x squared times the derivative of the inside. And f prime of negative x squared is e to the x applied to negative x squared, which gives me e to the negative x squared, and then times negative 2x. Just like that. Does that make sense? Good. Let's do some more. Help me out here. This function shows up a fair amount. What is the derivative of x e to the negative x? Where do I start?
Constant.
Yeah, got a product going on. Tell me how to get it.
Like x times d over dx. Plus d over dx. X minus
Exactly. All right. Clara, take the left-hand term. what is the derivative of e to the negative x?
Negative x, e to the negative
Close. Okay, yeah. So instead of doing both chain rule steps at once, go one at a time. So we'll do outside first, which is exactly the exponential, times the derivative of the inside. Yeah. Oh, I see. You were combining this with that. Oh, you were exactly right then. Good. Because the derivative of negative x is, of course, negative 1 times x is negative x. Now, second term. Mark, you're up.
1 times e to the,
Which is just that. And so we end up with this situation right here. Notice that this is a really interesting kind of result here. The derivative of x e to the negative x turns out to be negative x e to the negative x plus another e to the negative x. So it's sort of multiplying terms as it goes. Good. Very good. Uh-huh. Oh, do we have to factor it? That's a great question. So factoring is sometimes profitable. You don't necessarily have to. But we do have a common factor of e to the negative x. And if I factor it out, I get negative x plus 1. This would be useful, for example, if I asked you, where are the horizontal tangents? Where are the horizontal tangents? And so exactly as you said, we would set dy dx equals 0. And in factored form, that's particularly useful because I can now say that either e to the negative x is equal to 0 or x equals 1, right? Now what about this equation e to the negative x equals 0? Exactly. That's right. There are no solutions because when I look at the graph of y equals e to the negative x, it looks exactly like this with a horizontal asymptote, y equals 0. There are no solutions. Now, you may ask, how come the graph looks just like an exponential with a base less than 1? Because it is. Take a look here. What is e to the negative x anyway? Well, that would be the same as e to the, let's do it like this. E to the negative x would be the same as e to the minus 1 to the x power. Yes? And e to the minus 1 is the same as 1 over e. So that you can see that when I have a base bigger than 1 raised to a negative exponent, it is the exact same as having a base that is between 0 and 1 raised to a positive exponent, because a negative exponent indicates reciprocal. So this is y equals e to the negative x, which is the same as 1 over e to the x.
So it's 1 over 2 fourths.
Yes, exactly. So it would be somewhere in the neighborhood of about 0.3. What's that? Yeah, I can move up. Well, great questions. Tomorrow we are going to explore the general bases besides E, and maybe then I can do my history lesson.